Okay, so in this video we're going to practice. We're going to practice doing. We're going to have a little play around. So the idea is I want you to watch this video, and this will help you prepare for what's going to come ahead in tomorrow's lesson. Okay, Z is equal to cos theta plus J sine theta. Okay, standard. This is polar modulus argument form. The modulus of this complex number is 1, the argument is theta. Okay, now we know that Z to the n is going to be basically cos n theta plus J sine n theta using Demoivre's theorem. Okay. Alternatively, if we have Z to the minus n, it's going to be cos of, well, no, this is interesting. It's going to be minus n theta plus J sine minus n theta, which in turn, well, because cos is an even function, cos of something negative is just the same as cos of that something. And sine of something negative is the same as minus J of sine of that something, because sine is odd and cos is even. Okay? So we've got Z to the minus n is cos n theta minus J sine n theta. Now, if we look at this one, and we're going to add these two expressions together. Okay? So, Z to the n plus Z to the minus n, that's the left-hand side, is going to be equal to 2 lots of cos n theta. J sine n theta plus minus J sine theta disappears. Therefore, we get the result. We get the really important result that cos n theta is equal to Z to the n plus Z to the minus n all over 2. Incredibly important result, this. Because what this is going to do, it's going to help us express. I mean, last lesson we looked at, okay, if we had cos of 5 theta, how could we make this into basically sums of cos thetas? Okay, that's what we looked at last lesson. What we're going to do today is look at the other thing. If we've got cos of 5 theta, how can we write this as sums of, theta plus 2, cos 2 theta plus cos 4 theta plus cos 5 theta, so on and so forth. So that's what I'm going to do now. Okay, hopefully it will become clearer once we do it. Okay, what we're going to do is we're going to express cos to the power of 5 theta in terms of multiple angles. Now the key here, always start off with Z cos theta plus J sine theta. Standard. It's kind of like a standard thing to do in any of these complex number problems. Okay. Now, from that, and from our formula here, if we replace n by 1, we know that cos 1 theta is Z plus Z to the minus 1 divided by 2. Okay? Now, rearranging that, I'll get 2 cos theta equals to Z plus Z to the minus 1. Now, we want to express cos to the 5 theta. So what I'm going to do is I'm going to put both sides to the power of 5. So 2 to the power of 5 is 32, and we get cos to the power of 5 theta is equal to Z plus Z to the minus 1 to the power of 5. Okay? Now, we're going to expand this right-hand side using the binomial theorem. Now, that doesn't become too hard. It's the 5th row, so 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Okay. So we get 1 lot of Z to to the power of 5. That's not a problem. And we get 5 lots of z to the 4, but we also get 1 lot of z to the minus 1, plus 10 lots of z cubed, z to the minus 2 now, plus 10 lots of z squared, z to the minus 3, plus 5 lots of z, z to the minus 4, plus z to the minus 5. Okay. Now, if you want to pause this video, digest this line, okay, and then you can convince yourself of it. Now, we can simplify this. Z to the 5 plus 5 lots of z cubed, plus 10 lots of z, plus 10 lots of z to the minus 1, plus 5 lots of z to the minus 3, plus z to the minus 5. Okay? Now this is lovely. This is absolutely lovely. Because what I'm going to do, I'm going to put the powers, similar powers together. By similar powers, I mean here we've got z to the 5 and z to the minus 5. Okay? So here we've got z to the 5 plus z to the minus 5 plus 5 lots of z cubed plus z to the minus 3 plus 10 lots of z plus z to the minus 1. Now this is really lovely, this is. Remember, cos n theta is equal to z to the n plus z to the minus n all over 2. Okay? So that means that 2 cos n theta is z to the n plus z to the minus n. Now, here we've got z to the 5 plus z to the minus 5. That has to equal 2 lots of cos 5 theta. Here we've got 5 lots of z cubed plus z to the minus 3. This has got to equal 2 lots of cos 3 theta. This has got to be 2 lots of cos theta there. Sorry, that's cos 3 theta. Now, making this look a little bit nicer and bring back our left-hand side, remember that we had 32 cos to the power of 5 theta is equal to 2 cos 5 theta plus 10 cos 3 theta plus 20 cos theta. Now, if we divide by 32, we get 16 cos 5 theta plus 5 over 16, 5 over 16 cos 3 theta plus 10 over 16. I could simplify that a little bit more, but I'm not going to because I could just write this a little bit nicer. Cos 5 theta plus 5 cos 3 theta plus 10 cos theta all over 16. And there we have it. Okay, we've expressed cos to the power of 5 in terms of multiple angles. Okay, and this is, you know, a kind of typical exam question. It's the other way of what we did before. In the other lesson, we found that cos 5 theta is equal to basically 16 cos to the 5 theta minus 20 cos cubed theta plus 5 cos theta. This is what we did today, effectively. And notice the difference. It's just here, with what we did today, cos, we're expressing a multiple angle in terms of powers. Here, we're expressing a power in terms, here, we're expressing a power in terms of multiple angles. Whereas today, we are expressing a multiple angle in terms of powers. Okay, so it's the reverse problem. You need to use binomials theorem and everything else. Now, what I'd like you to do before today's lesson, remember that we had z to the n is equal to cos n theta plus j sine n theta, and z to the minus n is cos this time, what I want you to do before the lesson is to subtract those two, and I want you to get an expression for sine theta, sine n theta, similar to what we had with cos. Now I'll give you a clue, J is involved.